yet. Got it. Yeah. So yeah, the Hadoop system, right? As we discussed, it is a distributed monolith or a distributed system, and we have, we store files in block storage. We have a fault tolerant system. Even if the nodes fail, we can the Hadoop master or name node can replace it, uh, with a new node and copy the data or replicate the data. It is highly scalable as when we require nodes. As and when we require to increase the storage, we have, we can add a node, a worker node here, and then we can increase the storage, right? It follows write once and read many model, or worm model as we call it. And we have, this, these are the, high level properties of a Hadoop file system. So today we are going to, like, look about a fundamental aspect, that is, why do we need to store data as blocks? Like, why do we need a block storage in the first place, right? So let's assume that we are, storing, uh, this is a 500 MB file, and we are storing this file as is, right? Not block, but the whole file as is, right? This is a 500 MB file, and we are storing as is. This is fine, right? We can, let's say, if we are taking a minute to read this file into our query engine or into our processing engine, right? This is fine, because we are not expecting this, system, this distributed system, to perform as in par with any databases, right? That's not how these systems function. These crunch a lot of data, and we don't expect, or at least, when these systems were built, we didn't expect them to perform like, super fast as much as, any databases of the world, right? We expect they are, processing a lot of data. So, 1 minute is not a bad time. It's not great either, but it's not a bad time, right? But instead of, we have, and, we have to store, uh, we assume that, this would be one single entity and we are storing it in one worker node, right? But let's say I have a terabyte file, right? I'm just assuming it. It is not, like, not impossible, but we can have a terabyte file, right? If I want to read this file, let's say it takes 10 minutes, right? The problem is not the 10 minutes. The problem is that this worker node had to do all the, work of, reading this file, maybe processing this file, and then, giving the result and storing it in the file. Meanwhile, all of these other nodes will be staying, idle, which is not a great distribution of work, right? Let's say, we are paying, like, for 6 nodes or 5 nodes here, right? We are paying the bill for 5 nodes, and we are only having one node here that is doing all the heavy lifting, which is not good, right? How can we distribute the workload among these nodes equally? The answer to it is that we can have replica of the same, data everywhere, but, I can, use this terabyte file and store here and here, right? Which is fine. But even then, the workload might not be equal to, that might not be like equally distributed, because at any given time we are going to, like, process only one file, or, store or append or do any one replica of this file, which again, like, has its own, this one, the data can be corrupted, the node goes down. There are a lot of other issues that comes with, storing a file in one node and then expecting everything to go fine over the period of time, which is not a great look on our, setup, right? So what we have done is, since we already established that Hadoop clusters are made, or, like ideated on commodity hardware, right? That is the underlying feature here. It's not that we are using commodity hardware right now, but these systems are devised on, the first system, these built on the first examples, or, the first, like, ideation of these systems happened on commodity hardware. That means that we can have any failures that we are seeing here. Maybe my application itself has bugs. Maybe the hardware that I'm storing here, just corrupted my data, or even, kernel level issues, OS level issues. Like, there can be anything that can, just knock this file out at once. So we don't want to do that. So Instead of that, what we did is we kind of, like put chopped up the files into 128 blocks of each files into 128 MB blocks, and then spread across different um, nodes. That means that even if some parts, let's say my B4 and B3 blocks have completely wiped out, all right, from these two machines, I would have B3 and B4 here, and I can send that to these nodes or new nodes that are coming in places of these. That is very much easier rather than me transferring a terabyte data into the next node that is newly launched in our system. Moving a terabyte data is not always a good idea, or moving large amounts of data between nodes is not always a good idea, because networking is the one of the precious commodities in the entire uh, you know data centers basically. And this, which is also the case for our Hadoop cluster as well. We don't want to like use up all the network or use up all the storage, or just try to like hammer one machine with all the data, with one storing as single file. So we don't want to do that. The idea is to like scale the system as easily as possible, without any failures. So storing it in blocks has its own advantages. It has its disadvantages, but we will discuss about them in the later on, right? So the advantages here being that we are not clogging up one machine, nor we are not putting strain on one machine to store all the data every time. And if somebody wants to like read some parts of the data, we are not just trying to load the whole file into the memory of the client. So this is one advantage to having blocks, right? It is slightly more resistant or slightly more robust in terms of setups. That's why we use blocks, right? And if I want to run any query, right, or if I want to do any processing on it, right, I can send my program as a client to this particular master node. And what this master node can do is it can propagate this particular program to every single node here. So the same file which have been stored in one machine, it will have its resources exhausted on one node, but the rest of the nodes are sitting idle, right? Now, instead of going for one single machine, we are sending the same program to different nodes here, so that they can all work on the same workload, same data, but different parts of the file, and then they can get result almost around the same time, which reduces the you know amount of time to wait. Like I don't need 10 minutes to load the data. I can just have every single node load in 2 minutes, and then I'm good. 2 minutes is fine, right? Instead of 10 minutes. I am resistant to failure, because if there is any issues on the node, the driver node will again come here and check whether this particular node is doing fine or not. It will replace the node if not. So there is a mechanism for this. It is called heartbeat mechanism. So this is what is happening all the time, right? So this is slightly better approach in dealing with large amounts of data that is spanned across multiple nodes, as we saw here. Any questions, doubts? I'll just stop here for a quick minute. Okay, I'll take that as a no. So now this is what the idea of storing blocks was first conceived by you know engineers at Google basically, and they have came up with this solution, right? The main workload that they were seeing is they are loading a lot of data from the web scraping that they were doing in Google, right? And what they did was the type of workloads they were doing is they're dumping a lot of data on each of these nodes, and then the nodes and the Hadoop file system itself is capable of like chopping up these data into 128 MB blocks, or earlier it was only 64 MB blocks, but then the later versions of Hadoop adopted as 128 MB. The Hadoop V1 had 64 MB blocks, but the Hadoop V2 onwards, it is 128 MB blocks, right? So the Hadoop file system has logic built into it, so that anytime we are like dumping a lot of data, and this is just, as I told, right, this is write once and read many times. So we are writing data once in our raw layer within this particular file system, right? And same thing was done by Google as well. What they did was they observed that we are writing, especially in writing workloads, it is append and overwrite, or write, basically. These are the two main type of workloads that they are seeing, right? So for these kind of systems, block storage was suitable. So that's why we were seeing block storage, and write once and read many times model was successful for them. So how does writes work? Okay, first we will see about reads. That's what I've illustrated here, and then we will talk about writes. Following that. So as we discussed earlier, right, there is a metadata table, right? So when we are storing the data here, right, these nodes will not have idea as to what kind of data that we are inputting here, or which file it is. These nodes itself don't have that idea. They will have the file system defined for them, but they will not have any idea that what type of block this is, and which file or which folder these belong to. That is handled by metadata in the name node, right? The design of this metadata is interesting, because all the operations that you want to do, right? Let's say I want to read a file. Okay, read a file, or I want to write a file, right? So these two operations, right, even delete, or update, not update, delete also, these require a specific location to be specified, right? These require a location to be specified. How do you get that? Because we have only blocks here. We don't have the full file to define that, okay, this particular file has this name and this location. That cannot be done here, right? We cannot store this one here on these nodes, because the synchronization itself will be like too much of work. So we need one place where we want to store the data. That's where this master node comes into picture, or the name node comes into picture. So what does this name node do? It creates a metadata table. This metadata table will be stored in RAM of this machine, right? Okay, I'll explain why, but it is stored on RAM. So what does this have? Does it only have location? Just the file location? No, it has several different things, right? So one is basically your node, node details, like node 1 2 3, like worker node 1 2 3, right? This one. Basically, these are IP addresses. Okay, IP addresses of this file. I'm just for brevity, I'm just using one, right? This is some IP address here. So these are all like machines, right? These are all Linux boxes basically, and we are connecting over a network, right? That's why we have arrows here. So when we are connecting over a network, we need an IP address of the each of these individuals registered in this particular master node or name node, right? And that is stored in metadata table as well, right? We have this one location. Okay, we have block name, and we have hash. Okay, block ka hash, right? So basically what it means here is that, okay, in this IP address, in this location 1, I am storing block 1, and this is the hash of it. Okay, why do we need hash here? That means that, let's say I have a block 1 here as well. How do we know these two blocks are the same blocks? These two blocks are the same blocks. How do you know that? How are we sure? How does a computer identify, or this particular name node can identify these two blocks or the same blocks, because we said, right, any client can, read the data here or write the data basically. So they can also modify the block one, right? We will talk about that in writing part. So to identify that this particular, block is the block that we are looking for, and which has the, we can guarantee that, okay, this block has the data that we last inputted. So we create a hash out of it, right? Hash function is basically, you will do an input to a function, okay, to a hash function, and then it will give us some 16-digit representation of it. So this one, whenever we, want to know whether this is the, correct file or not, we are inputting the file here, and then the file will go to the hash function, and then it will be some hash function will give us the output. So that output we are putting here. So anytime we check, whether this block one is the same across the nodes, we'll just, do the same thing. We'll, do the hash function. We'll compare it, whether it is correct or not. We'll check according to the one that is stored here. If it is not, it is corrupted, it will be replaced again. So that's the fundamental, understanding of how this block, integrity works, right? So that is happening with the master node storing the data, metadata about it. So again, this is location one, block two, and here we have the same, hash two, right? This is a different hash because this has different set of data. Basically, that's what it is, right? So we have, hash table built in, and this will be in the RAM of the master node, because we want the metadata lookups to be really, really, really fast. Again, this could be a database table, right? Within this master node, we can have a database table, right? A database running that has, this particular, data stored in it. And what we see here is basically that, the block information of all the data for a particular file, right? Within this location, we have a block, and this is the hash. So every time, right, every time that we want to, do any operations on the files, this information is really, really important. Unless we have, this is like a map, right? This is like a map to a new city, right? Unless we have this information, right? Even if you have 100 different nodes here, they will be of no use. Okay. So as soon as the Hadoop cluster is started and all the nodes are registered and we have data in it, this will be created by your master node. That is the job of master node. Okay. And after which it will, start pinging these particular nodes here to check whether they are alive or not. That is called your heartbeat mechanism, right? So it will also periodically, it will check whether these blocks are, correct or not, whether, these nodes will check, and it will provide a report to it. That is called as a block report. So we have discussed this earlier. So now when we want to, read any data, what we are doing is we are sending a, as a client, let's say this is your app. Okay. This is your app or a process or an ETL process. Okay. Or an ETL or ELT process, where you want to read or write data from this particular, storage system, right? When you want to send data, sorry, when you want to send a request to write, so what it will do is it will go to first the name node, and it will come to this particular, metadata table here, right? Because the client, has no way to identify where we have to write the data, right? It has to get the, like this metadata information from that particular name node. If the location doesn't exist, the name node will create one for this particular client, but we have to know the metadata in the first place, right? So that is where this particular, metadata table comes into picture. Okay. So this is really important, by the way. So whenever we are trying to read or write any data, the first order of operation is that it will, query your master node for the data that you are looking for, the location that you are looking for. So if it is existing, it will give the location as well as, the block information. If it is not, then it will create a new location for us, right? So that is the first request and we will get the metadata. So this is the first step and this is the second step. So once this client gets the location information, right, it will cache it here, right? It will cache it. For further operations, they don't have to go through name node. They can directly go through worker nodes. So once you have the data or metadata from the file system metadata of this particular node, it will directly go to my nodes. Let's say I want to read block 3 data or any location data that from all of these nodes, right? So the location would be like this, location 1, directory director 1, and within this is file 1. So this is my location that I am looking for, right? So the first, it will get the this the client will send the yeah, the client will send the request to name node. It will get the metadata of where this particular file is located, and then it will, let's say we are having this in node 3, right? So this will go to node 3 and then or worker 3, and then it will get the data. So that's how our read operations work. Am I clear here? Somebody give a thumbs up. Okay. Uh, very quiet crowd. Cool. So now, once we have, this is how the like reads work in HDFS, right? So there are other aspects to how the master node or the name node manages the metadata, right? So why we want, before going there, why we want, RAM here? Why the master node stores the metadata in RAM? Because we want to, we want to have the metadata operations as quick as possible. We know for a fact that OLTP systems or databases, right, they are very fast in information retrieval, like small information retrievals, right? Let's say I want to retrieve user profiles. Yes, databases are good for it. So the same use case we can apply for masternode as well. So this is what masternode is good for, or any database is good for. So we are basically spinning up a database here within the masternode, and then we are saying that okay, store all my metadata information here, and then we are good. We will go ahead and like serve as many clients as possible. It's not just one client. We will have hundreds of clients going in and checking for the metadata all the time, right? So we want to serve these clients as quickly as possible. So yeah, we use you know a metadata location in masternode. Without a metadata like table, there is you can store like it's like a moot point to store any amount of data in the cluster, because nobody knows how to access it or where to look for. And they, these are not full files, so nobody would like can decipher what's going on here basically without that. So that's what this one is. So now that we understood reads, we will like check for writes, right? So what happens when we are trying to write? Same thing, like again the metadata operations require remain the same, 1 and 2, right? So what comes next, right? Anytime you are trying to write, right, you have to create a record even before you actually do change the data within the node. Okay, I'll explain why. Right? Suppose you are a client. Okay, you are a client who is doing an ELT operation. That means you have extracted the data. Now you have to load this data into a node. Sorry, into your cluster, basically your HDFS cluster, right? So this is your operation basically. So when we are trying to write this data, right, there are a lot of things to consider here. Since this is a distributed system, this is not going to go in one single place. This is going across cluster on different machines, because as we discussed, right, there is a replication factor involved here, right? What is the replication factor? Replication factor may basically is when you are trying to like write data in a Hadoop cluster. By default, it will make 3 copies of the data so that it wouldn't lose your data even if there are node failures constantly. So any data that you store by default on a Hadoop cluster stays in 3 copies, right? So now when you are trying to write the data, that means that you are, if you are like, rewriting or overwriting or, writing something, you are not writing once, you are writing thrice, and you are writing across 3 machines here, 3 copies in 3 machines. So the coordination required is slightly different than a single database that we see here, that we see in that we might have known, right? In a single database, what happens is you will have a table, you will just append data, or you will, do some operation like CRUD operations, right? Create, read or update and delete. These operations are very common in databases. Once you are, when you are trying to do in a single node database, right? It is like one table, one operation, or, one place you are editing that and you are done. Or if you have, have write constraints, you can write in one place, and then the database will take care that whether it is the correct, way of writing it or not. But in Hadoop, there is no way. Like, you're just reading files, you're writing files, that's it. There is no control mechanism as such, right? In databases, we have some control mechanism. It checks the rules first and then it will let you write. But in Hadoop or any like warehouse, there is no way that it is like, it's different. It enforces rules on read, but in databases, it enforces rules on write. Right. So any foreign key, primary key constraints, all of this, this will happen, while the data is written. Here, it is not the case. When you are writing the data, when you have written the data, it's fine. You can write anything, any garbage, or at least earlier it was the case, right? Now, when you want to read the same, data that you have written, which doesn't necessarily like have any constraints, right? So that's when the problem arises. It will not let you read because it found some discrepancies on it. Right. You have to be really careful what you're writing for. Now, since we have discussed, 3 copies, 3 machines, and all of that. So the first operation that, when you're trying to write, it will remain the same, which is like, getting the metadata information of that. Let's say if the file or the location doesn't exist, which is fine, right? It will, the metadata table will create a new, like entry here and say that, okay, location 2, and then, this is node 1 and this is block 1, and then it will, like hash n, some hash, right? It will do that, and then it will add, metadata entries for all the blocks. Let's say we have only one block, so it will like create 3 blocks and, have entries here, right? So that is how it will be done, right? But even before we do directly dump the data into HDFS, we want to create a record of the change that we are going to do in this particular location, location 2. Why we need to do that? Anyone has any idea? This is like lot similar to what databases have been doing for years, even even decades for that matter. Anyone? Okay. So because let's say, this data, the metadata that we are seeing here, it is stored in RAM, right? That means it is volatile. If something happens to your name node and, the data, is just lost, the metadata entries are lost because it is in RAM. It is a volatile memory, right? So what happens in the volatile memory is that as soon as the machine shuts down or there is some issue and we have to shut down the machine, we can copy this data, but sometimes, there will be chances that it's not possible. Like, your data is lost. So if some client is writing the data and some client, at a location 2, and the other client is expecting that, the client 2 is expecting that data at that location, right? And there has been some changes to your, like the file to block 1, right? B1 of file 2 is present in a node, and this client is trying to, like, get metadata information from this particular, name node. it will not have it because it was only on the RAM and it got vanished when the node had to restart. So this is a huge problem, right? Like the customers who are trying to, sorry, the stakeholders who are trying to get the data, if they can't find the data here because the name node had messed up, or because the name node hasn't stored the data properly, it's a huge problem. They will like lose trust on this whole system itself. It doesn't matter how fancy your setup is, how great your technology is. If a stakeholder doesn't find your data, gone. That's how data projects fail. That's how technologies fail, basically. So to avoid that, what they have done is they have done something called an edit log. So even before I dump my data here, so what I will do is you know, there will be a log on disk. This is on disk, by the way, because disks are durable. RAM is not durable. This is a non-volatile or durable place where you can store the data. So this is a log. What it will do is the client will say, you know uh, as soon as the write request is accepted, it will make an entry here of saying that okay, in location 2 I am going to dump the data of this file, right? This is an edit operation to the metadata table that will be stored in your edit log. Okay. In databases, it is called as val or write ahead log. Before you do any write or do any commits on write, it will be written onto a like val or write ahead log. So something similar here called edit log, right? So this is how we start the write process. Once we have the entry here, we can go ahead and the client can send data to nodes at that location. Any doubts here?
So this write-ahead log is stored in the client side, not on the master node?
No, it is stored on master node.
Okay, but it's
It is
stored on the
stored on,
disk.
yeah, it is stored on the disk.
Okay.
Master nodes disk, like as a file, like as a no, like for simplicity of explanation, as a text file, basically as a log file.
So the master node itself takes care of it when it receives a request?
Yep. Yep.
Okay.
Yep. Right. So this is how it is done, because we don't want to miss any changes that are happening to our metadata or our data. Basically metadata here basically means our data, right? Like the state of our data, basically. Maintaining state, the accurate state of our data that is spread across multiple machines is one of the most important aspects of this particular system. So how Hadoop does is by this way. This is inspired, partly taken from tried and tested things called databases, basically, right? So why do we need to maintain this log? Why do we need to maintain this log? I'll give you an example. When you're watching cricket, right, if you have went through any websites like crickbuzz or espn cricinfo, what they will do is they will have a score displayed, right? Scoreboard. Okay. They will have a scoreboard displayed here. And if you scroll down, they will have a log of each and every ball that is happening. Scoreboard basically is 30 for one in 6 overs. Okay. This is my scoreboard, and who is bowling and who is batting. Okay. This is the current state of my game. But how it happened? The first ball, it was a dot ball. Second ball, it was a 1 run. Third ball of the first over is a 4 runs. Right? Fifth ball, it was a wicket. Right? So we are keeping the log of all of these things that are happening, right? Along with the commentary, of course. But we are keeping a log of all of this, right? So this is your edit log. Even if somebody like completely misses the whole game, like they lost the scoreboard, right? I can recalculate the whole scoreboard from ball 1 to nth ball, like sixth overs, at the end of sixth over. So we need to keep this edit log as securely as possible, as durably as possible. Okay, that will be present in our disk. That is why it is stored in our disk. Since we have to have lot of metadata reads all the time, right? And a lot of clients are connecting to our no our our Hadoop cluster for our file operations, right? That is why we have to store our metadata on RAM. Am I making sense?
Yes, yes.
Okay. So now there is one more concept called FS image, right? FS image is basically once you start this Hadoop cluster, right, and every node as this one. So your metadata table will not have anything there, or it will populate based on what we have in edit log and what was the previous FS image state. FS image is basically your scoreboard. This is your FS image. This is file system image. FS image means file system image. So file system image is the current state of the file, and your edit log is your basically ball by ball events that are captured in your like commentary basically. So this is what it is. This is how Hadoop cluster will make sense, right? Every write operation needs to be present on edit log so that when we want to know, okay, at this point in time, somebody added some data to this particular cluster, at this location. Okay. So now what happens when we, actually write the data, right? Like actually write the data, not like on nodes, right? This is all, master node and, metadata, all of these operations, right? So we are clear with that. We are, we went through file location, we went through like, file location metadata, FS image, edit log, all of this, right? So now what happens when we actually write the data? So let me just draw the this one. We'll continue this session next time as well. But yeah, so let me draw this once again. This is your master, and these are your nodes, right? So when we are writing this data here as a client, the all the metadata operations are done, all the FS edit log operations are done. When we are actually sending data to the nodes, so we have some location here. So what Hadoop master promises is that I will not give you the location, but I will handle your reads based on where you want to write. And once I write, I will give you a confirmation that it is present, that is location. So that is my guarantee, right? Basically that is called as offset. So what offset in file terms, like in disk terms, or this one, right? So normally when you are writing data in your hard disk, what happens is that you as a user want to write data onto your hard disk, right? Sorry for the representation, basically, yeah. But you want to write at some block. So your user program will say that, okay, I want to write this data at this particular offset. That means at this particular location here, right? And then your computer will decide, okay, you are going to write at this offset. So it will do that. It will let you, do that. So it will let you write your file here, right? That is not going to happen in in like Hadoop cluster basically, because we don't know what data is present. We will know where the data is going through our metadata operations, but will not like entirely show the user that, okay, your data is written at this particular place. That is not the case. You will like have the folder directory one, directory to all of this, file 1. Okay, these will be present, right? This is your metadata information. But after which point, where it is writing and how it is writing, it will handled by your nodes, right? And this information is communicated to master, and then it will be communicated to client. So instead of saying that okay, you have to write after a particular offset, like after a particular uh, like place in your particular memory, it will say that okay, I will write in a particular place in memory, within this particular one, on in my RAM or in my disk, and then I will pass this information to this one, rather than saying that okay, I am writing at this location. The user or this application basically will not determine where the data is being written in Hadoop. So Hadoop file system will determine the where the data is going on, and it will basically write the data there, right? So let's say we discussed about this 128 MB thing, right? 128 MB of blocks. So if my client is sending 1 GB of data right now, this is an ETL client basically. It is saying 1 GB of data at some location, right? Chances are that each block will exceed this 128 MB limit, right? Of course. So your master has to like say that okay, you have to like uh, you know go to this particular node and check. Okay, so let's say I have a block 1 already, which is you know uh, which is around like only 10 MB here, right? We have only one block for this file. So I'm sending 10 GB right now into the same folder, directory 1, directory 2, file 1, folder right now, right? So what happens here is that till 128 MB, there will be no issues, right? From 10 MB till 128 MB, there will be no issues here. After 128 MB, the like the worker node will send a request to name node saying that your write operation has failed. You have to acquire a new location, basically a new block, and then it will do a request. When it is doing a request, the master node will create an entry in our metadata table saying that okay, I am creating a new block here, block 2, and it will live at this location and all of this. So I'll do a metadata operation here, and then right, it will start with the next block for 128 MB. Okay, this is my first block 1. This is my block 2. Maybe on a different machine, uh, but this is how it will be done. So this is the write operation that we are seeing, right? This is for files that have only one block. So what happens if I have n blocks? Let's say 4 blocks: B1, B2, B3, B4, right? So each of these blocks again will have 3 replicas, right? There will be 2 replicas here. Okay, again, these 3 will be present in your different machines basically, right? So if I have to read or write to these blocks again for the same file, what Hadoop master will do is it will pick one block out of these from any machine randomly and says, okay, you are the primary block here. Okay, you are the primary block. Any updates that I'm going to do, or any deletes or anything that I'm going to do on you, or any writes on you, overwrites or writes or anything, right? You are the first one to receive the updates, and you will propagate these changes to rest of the blocks. So that is how the writes happen in Hadoop. So basically what it says is that okay, you are my primary block. Once you have my changes, the new coming upcoming changes from the client, basically an append or a write, overwrite. So I will do that to you first. Only then what you will do is you will propagate the same. Once you have done, once this operation is successful, I will send this block to, I will send you to other, places where you have the same block or you had this previous, state of the block. That is what will happen with writes. Any doubts here? Okay. So what if my data is not, you know, 128 MB? Let's say I'm writing only like, okay, not 128 MB. Let me put this case. Let's say I am, inserting 100 million records. Okay, 100 million records at once. Okay, let's say these 100 million records are around 1 GB, right? When we chop up these, records into blocks, let's say, like, of 128 MB, right? Do you like, we have to think about how these records are bifurcated, right? We cannot say that, okay, let's say my record has, like 20 columns, right? I cannot just, like have 10 columns in one block and, another 10 columns in another block, right? That is absolutely nonsense. Like it cannot happen. Like there is no way we can, put any queries or we can, make any sense out of it. Let's say you're, when you are trying to bifurcate 128 MB, now what happens if the, last, block, last record, doesn't, fully fit? What happens to that particular block here? So at the end, what it does is your Hadoop, so file storage, it will add some gibberish, basically zeros or some identifiable characters to make this block as 128 MB. This is called as padding, basically, right? This is called as padding. So why does it do? Because it doesn't want to like, create this scenario basically where half of your record is in one block and the other half is in another block. Nah, that's not going to cut it. So to avoid that, one record or the last records where you cannot fully insert one single row or one single quote unquote record will be made as zeros or some identifiable characters that Hadoop file system will recognize that okay, this is not the data that the user has inputted, but this is my own making, like my own, like gibberish or garbage. So I will not include this whenever this file is being queried. So this is a like dummy record basically. It inserts a dummy record and calls it, okay, this is my block. So that's how it is. So this happens, in a lot in appending. When you are appending the data continuously, right? What happens is the blocks, which are not 128 MB, right? So they will like, reach to that 128 MB limit. Let's say this is 100 MB. So they will reach to 120 MB, 128 MB limit. But sometimes it so happens that, we still have a lot of data to be written. So what really happens here is that we want to like create block size that is compliant with our Hadoop file system, but we don't want to like chop up the records, right? We don't want to chop up the records. So that is where we find ourselves in this padding situation. So this is the one of the best assumptions that best implementations that we could come up with, like doing this one. There will also be a lot of duplicates that will happen because sometimes multiple clients trying to write towards the same location, and it will create a lot of duplicate records. In most scenarios, Hadoop file system itself will deduplicate the data and then give it to us, because it knows that these are the traces from different clients being written at one place at the same time, and we can like dedupe the data. Even if we were to restart the write process after we have seen certain client failing to write, or certain hardware failure or some bug happened, right? It will have residual data. So what this Hadoop file system is have done is they have identified numerous clever ways to like kind of get us to get the system to identify that these are not the complete records, or these are not the good records, quote unquote good records to be present or expected by the user. So we will filter it out when we are reading the data. So this is how read, write, and every other process happens to be, like happens in Hadoop ecosystem or Hadoop file system, basically. Okay, I think we are at the hour, so I'll uh, stop the recording now, and we can go for the doubt clearing session or anything that you guys want. Let me stop the recording now.